Welcome to the ITSP Magazine Podcast Network. You are about to listen to the Cognition Podcast, a show about artificial intelligence and how it is transforming the world around us, with your biological, sentient, and mostly rational human host, Hutch. Knowledge is power, now more than ever.
Hello, everybody, and welcome to the third episode of the Cognition Podcast. As always, I am your host, Justin Hutchins, aka Hutch. And today we're going to be talking about the rise of Transformers. And to be clear, not the Transformers like Optimus Prime and Megatron, morphing automobiles, which only the likes of Shia LaBeouf can save us from. Instead, we are going to be talking about the Transformer architecture and how it is revolutionizing the world of artificial intelligence. Specifically, we are going to look at an area of machine learning that isn't often mentioned within the context of Transformers, and that is robotics. But first, let's talk about what Transformers are, their background, and what they're commonly used for. Historically, there were many types of deep learning architectures, which were each more or less effective at various different types of machine learning. Convolutional neural networks worked well with computer vision and image processing. LSTM, or long short-term memory, and recurrent neural networks were used for natural language processing. Generative adversarial networks for image generation. But in recent years, machine learning has largely begun to converge on a single type of architecture, namely the transformer architecture, which introduced a highly efficient and highly scalable design that has been effectively adapted to all sorts of machine learning tasks. In 2017, researchers from the Google Brain team published a paper entitled "Attention is All You Need." And within this paper, they proposed the transformer model, a type of feed-forward neural network architecture. This original paper presented the transformer architecture specifically to improve on natural language processing systems. At the time, the leading approach to natural language processing was to tokenize the input text, essentially breaking it down into smaller units, and then using recurrent neural networks, which had to process that tokenized input sequentially. Transformers improved upon that design by creating an effective way to process tokenized input concurrently. This was accomplished through the introduction of an attention mechanism, which established attention scores. Each token within the input is assessed to determine the significance of its relation to other tokens within the input. This new architecture effectively addressed many of the shortcomings of using LSTM and recurrent neural networks for natural language processing. In the years that followed, data and computer scientists began experimenting with transformers for other possible uses. A researcher from Google named Alexei Dasovitsky was working in computer vision, the machine learning discipline focused on image processing. And while trying to tackle challenges related to the scaling of training sets while using convolutional neural networks, he discovered that this problem could be effectively solved by applying the same kind of transformer architecture that had been used in natural language processing. That was what he referred to as the vision transformer. I'm now going to read briefly from an article published in March 2022 on quantummagazine.org. The success of Transformers prompted the AI crowd to ask what else they could do. The answer is unfolding now, as researchers report that Transformers are proving surprisingly versatile. In some vision tasks, like image classification, neural nets that use Transformers have become faster and more accurate than those that don't. Emerging work in other AI areas, like processing multiple kinds of input at once or planning tasks, suggests Transformers can handle even more. Just 10 years ago, disparate subfields of AI had little to say to each other, but the arrival of Transformers suggests the possibility of a convergence. End quote. Some of the latest and most impressive machine learning technologies, to include ChatGPT, Bard, Stability AI, and DALL-E, are all based on the transformer architecture. The transformer architecture is extremely efficient and lends itself to scaling. Models built on transformers have also proven to be exceptionally good at generalization. Within machine learning, generalization refers to the ability of a model to make accurate predictions or decisions based on new or unseen data. An example of generalization is if I ask DALL-E to create an image of Joe Biden riding a monkey up to the peak of Mount Everest. It is unlikely that a similar image existed within the dataset that was used to train the DALL-E model. But within that training data, there was probably images of monkeys, images of Joe Biden, and images of people hiking up Everest. The system is able to generate such an image because of its ability to generalize. Its ability to use connections it has made between language and imagery, and extrapolate from those connections, something that is not found within its training data. The output, an image of Joe Biden riding up a monkey up Mount Everest, is derivative of the training data, but it's also something that's uniquely new. So, given this convergence that we are seeing in machine learning, I recently started thinking about how mechanical robotics, which have largely been focused on reinforcement agents to date, might be falling behind. And it made me wonder, is there a way that the transformer architecture could be applied to robotics? I didn't have any immediate opinions on what exactly that implementation might look like. But with so many other disciplines benefiting from transformers, there must be a way, right? And after a brief search on Google, I had my answer. I found a fascinating article published by the robotics research team at Google in December of 2022. The article was entitled RT1, Robotics Transformer for Real-World Control at Scale. In this article, the researchers present a way to use the transformer architecture for physical robotics. Such a model could use natural language as input and effectively translate that to kinetic actions as output. I could tell it things like, get my wallet from the dresser, and the model would be able to translate that input into the requested actions, specifically opening a drawer and then retrieving a wallet from the drawer. To build a training set for this purpose, the researchers collected a series of brief videos of similar robots performing specific actions, and then correlated those video images to text describing those actions. As we have already discussed, the transformer architecture requires tokenization of data into smaller units. In addition to the tokenization of language and imagery, which we already know that transformers are exceptionally capable of doing, the researchers in this project also devised a way to tokenize the kinetic actions associated with those texts and images. I'm now going to read directly from that research publication. RT1 is built on a transformer architecture that takes a short history of images from a robot's camera, along with task descriptions expressed in natural language as inputs, and directly outputs tokenized actions. RT1's architecture is similar to that of a contemporary decoder-only sequence model trained against a standard categorical cross-entropy objective with casual masking. Its key features include image tokenization, action tokenization, and token compression. The article then goes on to describe the action tokenization. It reads, the robot's action dimensions are 7 variables of arm movement: X, Y, Z, roll, pitch, yaw, and gripper opening. 3 variables for base movement, X, Y, and yaw, and an extra discrete variable to switch between 3 modes: controlling the arm, controlling the base, and terminating the episode. Finally, the article goes on to describe the training process. It reads, to build a system that could generalize to new tasks and show robustness to different distractors and backgrounds, we collected a large and diverse dataset of robot trajectories. We used 13 EDR robot manipulators, each with a 7-degree of freedom arm, a 2-finger gripper, and a mobile base to collect 130,000 episodes over 17 months. We used demonstrations provided by humans through remote teleoperation and annotated each episode with a textual description of the instruction the robot just performed. The set of high-level skills represented in the dataset includes picking and placing items, opening and closing drawers, getting items in and out of drawers, placing elongated items upright, knocking objects over, pulling napkins, and opening jars. The resulting dataset included 130,000 plus episodes that cover over 700 tasks using many different objects. End quote. So the end result of this experiment was extremely promising, to say the least. The model was evaluated within the context of 4 different types of tests. It was tested on performing seen tasks, tasks that were comparable to the specific tasks it was trained on. It was also tested on unseen tasks. These were tests to evaluate its ability to generalize from its training on completely new and uniquely unseen tasks. It was also tested with various changes to background and scenery to ensure that the system's effectiveness was not strictly contingent upon environmental conditions similar to those in the training data. And it was tested with various distractions occurring in close proximity while performing the tasks. In all 4 of these evaluations, the model significantly outperformed the 3 other baseline models it was tested against. Unfortunately, while this worked well within a controlled setting, it's still not easy to scale. Unlike other modalities that transformers have performed exceptionally well in, the training data for robotics is not simply available for the taking. There are hundreds of terabytes of text and image data all across the internet, just waiting to be scraped and aggregated. But that isn't true of data pertaining to kinetic robotics. In this exercise, all of the data was created manually and created by a team of operators working tirelessly for over 17 months. Nonetheless, despite these constraints, this research does demonstrate that, like many other disciplines of machine learning, the future of robotics may also lie within the world of transformers. And the frequent improvements that we are now seeing in implementations of the transformer architecture may be bringing us one step closer to having robots walk among us. For some, that might be exciting. For others, that might be terrifying. Personally, for myself, it's probably a combination of both. This convergence of machine learning is itself becoming a technology accelerator. Innovations and breakthroughs in any one discipline of machine learning now constitutes a breakthrough in all areas. In the coming years, technology will begin to rapidly transform our lives in ways that are unlike anything we've seen before. It will likely be exciting, strange, and at times even frightening. But above all, there's one thing that we can be sure of. Things are about to get weird. And that's all for today. As always, this is Hutch, broadcasting from the last bastion of the human resistance. Thank you all for listening, and we will catch you on the next one. Over and out.
We hope you enjoyed this episode of the Cyber Cognition Podcast with Hutch, part of the ITSP Magazine Podcast Network. If you learned something new and this conversation made you think, then add this show to your favorite podcast player. Subscribe to the ITSP Magazine YouTube channel and share the ITSP Magazine Podcast Network with your friends, family, and colleagues. If you represent a company and wish to connect your brand to our conversations and our audience, visit itspmagazine.com to learn how to sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey.